Hi everybody, thank you for joining me in my first ever video lecture. I hope this goes well. Today we're going to cover chapter 10. We need to finish that chapter up. We're going to talk about limiting reactants, and we're going to talk about energy for a little bit, which is in a subcategory called the heats of a reaction, and we're going to use stoichiometry to solve some of our problems. And then we're going to start chapter 11. We won't get through nearly half of it, which covers the material on a quantum mechanical model of the atom. So our first topic is called limiting reactants. A limiting reactant is the reactant that gets completely used up. And another reactant might be in excess. So it's not completely used up. There's going to be some left over. So here's an example of that. We have carbon and it's reacting with oxygen to make a CO2 molecule. This is a 1-to-1-to-1 relationship between all the reactants and the products, which makes it really easy to understand the concept. Let's say we don't have one carbon. Let's say we have 3 carbons, and let's say we don't have one oxygen. We have 2 molecules of oxygen. Imagine what happens when they react together. The amount of oxygen is going to limit how many CO2 or product molecules that we can make. Since it's a 1-to-1 relationship, we are limited by 2 oxygens to only make 2 carbon dioxide molecules, which means if oxygen is the limiting reactant, then carbon must be our reactant that's in excess, meaning there's going to be enough to react with all of the oxygen, plus there will be some left over. So remember, up until this point, we have had a reaction with one substance reacting with another substance, making a product of some sort, maybe another product. And what you know so far is that you're given the amount of one of these. Let's say you're given the amount of A, and you're asked to calculate either the amount of B that has to react with it, the amount of C that is produced by it, or the amount of D that is produced by it. So let's say that you're asked to solve how much of C is made from a certain amount of A. Up until this point, we have assumed that there was enough of B. Another way to write enough is to say that B was in excess, which makes A considered a limiting reactant. We didn't call it that because I just wanted you to pay attention to the fact that you had one amount and you were solving for another amount. We'll write our chemical equation again. We have some information. We know we have 129 grams of this, and we have 381 grams of this. We have 2 jobs. One is to figure out how much product we're actually going to make, and the second is to figure out which of these is the limiting reactant. So we need some other information. We need the molar mass of each of these, which we get right from the periodic table. Antimony by itself is 121.8 grams per mole. Iodine by itself, diatomic molecule, 253.8 grams per mole. And SbI3, 502.5 grams per mole. So our strategy is going to be, we're going to take the first one and calculate how much product. Then we're going to take the second one and calculate how much product. 129 grams Sb. I need to multiply that by in every 1 mole of Sb. There is 121.8 grams. That's just from here. I'm just going from mass, turning it into moles. Then when I have the moles of Sb, I can make a relationship between those two and those 2 moles. So there are 2 moles of SbI3 in every 2 moles of the Sb that's in the chemical equation. If I'm keeping track of units, I see a surviving unit is moles. So I've just calculated how many moles of this, but I don't want that. I want grams. So then I say there are 502.5 grams of the product in every 1 mole of the product. That's going to cancel there and there. And my answer is going to be 532 grams of product. Okay, we did that one. Now we're going to do this one. 381 grams of that reactant. We turn it into moles by saying 1 mole of it is 253.8 grams. We want now the relationship between this product and this reactant, which is 2 to 3. So 2 moles of SBI3 for every 3 moles of the I2. Grams crosses out, moles of I2 cross out. I've just solved for moles of this, but I'm going to turn it into grams. Say there are 502.5 grams of product in 1 mole of it. And in this calculation, I get 503 grams of product. So one of these is possible and one of these is impossible. So my strategy is I take the lower number and I say that is how much I'm going to make. Based on the fact that it is coordinated with I2. So we're going to call I2 our limiting reactant because it's this 381 grams that is going to limit how much product we make. And we're going to say that this one is in excess. The last part of the problem was to find the mass in grams of the element that was left. So the one that's in excess is going to have some left over. So let's solve for that. 2 antimonies plus 3 equals 2 SBI3. Remember that this was 121.8 grams per mole. This was 253.8 grams per mole. And this is 502.5 grams per mole. So we labeled this as our limiting reactant, and we said that this one was in excess. So what we want to do is use our limiting reactant, which was 301 grams. And we're going to figure out how much of this we need to react with all 381. We did calculate that we would make 502 grams of the product based on this. So now let's see this way. So we take 381 grams of the iodine. We use the molar mass from the periodic table. In 1 mole of iodine, there's 253.8 grams of iodine. Notice I just turned it into moles. Now I need the relationship between this and this, which is 2 moles of antimony in 3 moles of iodine. And I need it in grams actually because I'm going to be comparing it with grams. So 121.8 grams of antimony is enough to be 1 mole of antimony. And our answer is 122 grams of antimony. Now remember, the problem said there were 129 grams of antimony available. But we just calculated that if we had 381 grams of iodine, all we would need would be 122 grams of antimony. So there will be 7 grams that are not used up of the antimony. The next topic is thermochemistry. Thermo means heat. So we're going to study the heats of reactions. And we need to learn some of the units of energy. One is a joule. Another one is a calorie. And another one is a capital C calorie. These are all different. The only conversion factors we really need to worry about are that there are 4.1484 joules in every calorie. And the same number, you'll have this on a conversion sheet during an exam, is 4.184 kilojoules per kilocalorie. And what you need to remember is that a capital C calorie is the same thing as a kcal. Our conversion factors, we had two. 4.184 joules per calorie or 4.184 kilojoules in 1 kilocalorie. Those are the only two conversions that we used. Calculate the number of kilocalories, calories, and joules in 4.25 kilojoules. All right, so we'll start with that. 42.5 kilojoules. And let's just pick one of them. Let's convert that to calories. So what conversion? We could use either of them. Let's use this one. In 1 calorie, there's 4.184 joules, but we can't cross out kilojoules and joules, so we need one more conversion factor. How about there are 1,000 joules in 1 kilojoule? Kilojoules now cross out, joules cross out. Our surviving unit is calories. And in your calculator, you would put 42.5 times 1,000 divided by 4.184. So when we talk about thermochemical equations, we use a symbol like this. This H means heat, but it also is called this, enthalpy. This change here, this delta sign, is telling you that it's the difference of heat that goes into the reactants to break bonds apart versus the heat that's created when new bonds are made in the products. And there's a net effect. Sometimes you put more heat in, sometimes more heat comes out or is released. So we learn those as exothermic and endothermic reactions. What this is saying here is that if you have an exothermic reaction, your delta H, that little R means reaction, but your change in enthalpy is going to have a negative sign. And in an endothermic change, the enthalpy increases and it's going to have it won't have a plus sign, but it'll be a positive value. So here's an example of that. Let's say we have C2H6 and we react it with oxygen and we create 4 carbon dioxides and 6 waters. We can express the heat of the reaction, the whole reaction, as this. Delta H equals negative 2855 kilojoules. That means if we burn 2 moles of this, that's how much heat would come out. If we reacted it with 7 moles of oxygen, that's how much heat we would get out. This negative sign right here is not negative heat. That negative sign is telling you that it's an exothermic reaction. If you know that it's exothermic, then you can write the equation again. And this is a plus sign. You're adding the amount of heat to the product side because it's treated as a product if you're releasing heat at the end of a reaction. Opposite to that is when you have an endothermic reaction, and then you treat the amount of heat that's absorbed into the reaction as a reactant instead of a product. You could do it this way, where you say add the heat to the reactant side, or you can do it this way, where you have the whole reaction and then you report what the change in enthalpy was, 92 kilojoules for this whole reaction. Look how easily I could make any kind of conversion factor between heat and how many moles that I've created. This is saying 92 kilojoules of heat were needed to react 2 moles of ammonia. I have a conversion factor with heat here and moles here. I can do lots with that. Okay, this problem is asking what mass of liquid octane, which is C8H18, must be burned to create that much heat. Now notice, this delta H is reporting the heat as negative, so it's exothermic. 5,471 kilojoules of heat, but it's per mole of this. If it says per mole, you don't need the whole equation. You have the conversion factor. You know that 5,471 kilojoules of heat is coming off of 1 mole of C8H18. This question is asking what is the mass of this compound to get this much heat. So we take 9.05 times 10 to the 4th kilojoules of heat. We know there's a relationship where 1 mole of C8H18 can burn to create 5,471 kilojoules. And here I'm solving for moles of C8H18. I'm out of room here, but what I would want to do is convert that now to mass. We do it over here, 9.05 times 10 to the 4th kilojoules times in 1 mole and I need some information, the molar mass from the periodic table, which is 114.2 grams. So kilojoules, moles, moles. My surviving unit is in grams. That's what I wanted. And the answer is 1.89 times 10 to the 3 grams of this octane. Okay, so we're moving on. Chapter 11, Atomic Theory. This is the quantum model of the atom. But before we do that, I just want to review a little bit of what we've known and how it's benefiting us of understanding subatomic particles and atoms. Let's say we have some iron. And 91.7% of all the iron atoms comes from iron 56, from that particular isotope. And iron is element number 26. So what kinds of information do we have here? That's information about how many protons we have. This is information about how many protons we have, plus how many neutrons we have. So this side over here is a lot of information about the nuclear part of the atom. We could put a 0 here. That's information about electrons. It's the number of protons minus the number of electrons. So if we have 26 protons, we must have 26 electrons for that to be 0. We could have a situation like this, still have iron 56, still 26 protons in the middle. We could have a 2 plus, which means that we have 26 protons. If we subtract 24 electrons, that is how we get this positive 2. This is nuclear information This is electronic information, but we can take it a step further.
You are introduced to electron particles, and just like protons and neutrons, you learn how electrons are symbolized using letters and numbers. As you can see, keeping track of electrons is slightly more complicated than keeping track of protons and neutrons. The main difference is that protons and neutrons stay put in the nucleus of the atom. We just need to count and label them. On the other hand, electrons move around the periphery of the nucleus. Now, while the actual electron motion cannot be described by classical physics, we can describe the relative energy of each electron in that atom. Just as we symbolically represented protons and neutrons, we symbolically represent electrons using what is called an electron configuration. We write electron configurations not only to keep track of the number of electrons in each atom, but to understand the energy of each electron and where they are likely to be found around the nucleus. Because we cannot track the movement of an electron, we say an electron is likely to be found in some region of space around the nucleus, but not just anywhere. Depending on how much energy the electron has, the electron is limited to only certain regions of space around the center of the atom. These regions of space can be drawn into shapes, and we call them atomic orbitals. In this course, you will want to learn 3 categories of shapes. The easiest is the s orbital shape. This is just a sphere. An electron with this energy is likely to be found somewhere within the sphere. The next is the p orbital shape, a dumbbell shape with 2 lobes. Electrons with p orbital energy are only likely to be found within the outline of the shape. Additionally, there are 3 spatial orientations for the p orbital. One along the x-axis, one along the y-axis, and one along the z-axis. This makes 3 different p orbitals in 3-dimensional space, logically labeled px, py, and pz. The next is a d orbital. There is not one common d orbital shape. If an electron has d orbital energy, it may be found in any of these 5 regions of space around the nucleus. Even though they are different shapes, the energy for each of these d orbitals is the same for a solitary atom. It is certainly worth your time to try and draw each of these orbitals starting with a blank 3-dimensional coordinate system. When an electron is likely found within the boundaries of one of these orbital shapes, we often use the expression that the electron is in an orbital, or that an electron occupies an orbital. Said this way, we can state the rule that only 2 electrons may occupy any single atomic orbital. We also take a shortcut and use little boxes to represent the orbitals instead of drawing their shapes. We draw 1 box for an s orbital, 3 boxes for the p orbitals, and 5 boxes for the d orbitals. Then we can place 2 electrons in each box to keep track of them. There is an order to this. The electrons completely fill a sublevel before moving on to the next. Also, they fill up empty orbitals within a sublevel before pairing up with each other. Recall that the periodic table was set up like a calendar. Starting with element number 1, the number of protons increases by 1 each time we move from one block to another. That also means that as we step through the blocks, we can add 1 additional electron as we go from left to right. In this way, the periodic table can be used as a counting device for the number of electrons. Each block counts as 1 electron. Take carbon, for example, and count the blocks. 1, 2, 3, 4, 5, 6. Carbon has 6 electrons. So now let's assign these 6 electrons to the correct atomic orbitals. To do this, we divide the periodic table into regions. The regions will include the number of blocks which match the maximum number of electrons allowed in each orbital. The s orbital region has 2 blocks total in each row. Unfortunately, the first s block is split far apart for hydrogen and helium, but there are still only 2 blocks. Because there are 3 p orbitals, and each can have 2 electrons, there are 6 blocks which represent the maximum number of p electrons. The d block has 10 blocks for a maximum number of 10 electrons. Just keep in mind that the blocks on the periodic table are to count individual electrons. Like they keep track of protons, each block only counts as one. This should not be confused with the blocks we use to represent the atomic orbitals. In an orbital diagram, the 3p blocks represent the 3p orbital shapes. Placing 2 electrons in each illustrates that only 2 electrons can take up that specific region of space around the nucleus. The reason we use these blocks is to ultimately keep track of paired and unpaired electrons. This will come later. However, the main reason we use the blocks on the periodic table to keep track of electrons is because the periodic table is laid out to take into account how the electron energies are ranked from lowest to highest. We don't have to remember that a 3d electron is higher in energy than a 4s electron. The periodic table will keep track of this for us as long as we remember a few simple rules. We start to write an electron configuration by locating the element of interest and starting from block number 1. Carbon is here, so we assign each electron along the way to the correct orbital. We first write a number 1 to represent that we are in the first and lowest energy level. Then we write an S for the orbital shape. Then we count the number of blocks to the end of the section and put that number as a superscript, 1s2. Then we go on to the next row, period number 2. We write a 2. We are in the S section, so we write S, and we count blocks to the end of the S section, 2s2. Then we write 2 again, a letter P for the P section, and count the blocks until either we get to our element or we get to the end of the section. Count 1, 2 blocks, so we have 2p2. The electron configuration for carbon is 1s2, 2s2, 2p2. We can take a shortcut, and instead of writing the entire electron configuration, we can start with the element in group number 8, just before the row where we find our element. Helium is the noble gas we can start with, and then just add on the electrons in the featured row, 2s2, 2p2. Let's do an example like bromine. The element in group number 8 just before bromine is argon. So we start there, argon in brackets, and then we write 4s2. Now the work on your part is to remember that this top middle row is 3D. After the D block, we resume with the period number, which is 4. So 4p, 1, 2, 3, 4, 5. Now let's say we had a bromine ion, Br, with a -1 charge. This negative sign tells us that there is 1 extra electron. So the electron configuration would take into account the 1 extra electron by placing it in the next position, which happens to be in a 4p orbital. We add it here. We can also say that a bromine ion has the exact same electron configuration as this element here, krypton. When this happens, we say that the bromine ion and the krypton atom are isoelectronic. That is, they have the exact same electron configuration. We can work backward as well. Potassium ion, K+, has lost an electron. If the potassium atom configuration looks like this, and we remove an electron from the configuration, we see we are isoelectronic with the element argon. Allowing the periodic table to take care of the energetic order of how electrons are distributed around the nucleus is convenient, but we need to understand one more thing. The mathematics used to come up with these orbital shapes in the first place did so in a specific order which is not the same order as their energy. New subshell orbitals came out of the math every time the principal quantum number was increased by 1. So at the lowest energy level, n equals 1, the math will only produce an s orbital shape. If the electron energy is increased to a higher energy shell, n equals 2, 2 subshells are now possible, a larger s orbital and 3 different p orbitals. It isn't till n equals 3 that the math produces an even larger s orbital, 3 more p orbitals, and a set of 5d orbitals. So while it's possible to rank the electron orbital energies so that 3s is greater in energy than 2s is greater than 1s, and 3d energy is greater than 3p and greater than 3s, It's not so cut and dry to rank a 4s and a 3d orbital because those electrons take up different volumes of space around the nucleus, an S shape versus a D shape, and at the same time different shell energies, 3 versus 4. Fortunately, the blocks on the periodic table are arranged in a way that takes care of this 4s.